Hello, everybody. This is Dr. Keith Schubert. So, I've made up a little slideshow for you to kind of walk you through the ideas behind. Really, I want to get to independent component analysis, but to explain independent component analysis, it's usually a little easier to give a first introduction to principal component analysis. Partially also because we're going to use principal components analysis as one of the steps in ICA. You don't have to, but it actually makes things a lot better, and most ones do. So I think it's just helpful to kind of understand why they work. You will also see both of these in a lot of different areas. So being familiar with both is a very helpful kind of step in your understanding of things. So we'll first start off talking about PCA, and then we'll move to ICA. Right. So we're going to make an assumption here when we're dealing with PCA is that we're going to deal with Gaussian random variables. ICA is going to go to non-Gaussian, um, but you might ask the question, why is Gaussian such a big deal to us? And what makes the big difference? And this is actually the idea behind both of them, is this one idea that a Gaussian random variable that passes through a linear system will produce a Gaussian random variable as an output. It's kind of hard to overstate the importance of that. This is why we use Gaussian random variables all throughout engineering. So when people make those assumptions and you hear, oh, we're going to use a Gaussian random variable, this is why. So when you do digital signal processing and everything else, we deal with linear systems and linear approximations a lot because they work really well. And Gaussian random variables basically preserve their Gaussianness when they pass through. So this is a pretty crucial idea that's going on. Principal component analysis is going to therefore assume everything in the universe is Gaussian. You're kind of that steady state end position. Um, Let me show you kind of what this looks like, because we make this statement and you might say, well, what if I don't have Gaussian random variables? Well, if you consider here, I've shown you, take a look at the left side. That's a uniform random variable. So I just kind of made this quick inside MATLAB. I generated a whole bunch. I forget the exact number. I think I made something like a million or something, and then did a histogram of uniform random variables. So just a ridiculous number, right? Um, just literally like a million of these things, sorted them into a histogram into their area. And you can see it is pretty uniform. It's not perfectly uniform, but it's pretty darn uniform. Now, what happens when I take two of that same size and I add them together? I don't get a uniform random variable anymore. If you look at the second one down, that's two random variables, again, somewhere around a million each, and I just added them together. And when you plot them out, what you'll find out is that they're actually, I've centered these, so they're, if you look at the first one, it's from minus zero point 0.5 to zero point 0.5 instead of 0 to 1. Otherwise, it just creates an ugly skew. So I centered mine so it's nice and symmetric for adding them. Otherwise, it would just be over from 0 to 2 when you were doing it. Um, but in any case, this is kind of prettier, and you can see, hey, look, nice and triangular. Um, I didn't do 3, but I went to 4, right? So if I added 4 random variables together, if you look at that curve on the bottom, it looks pretty darn Gaussian, right? It's not perfectly Gaussian, but it definitely has that kind of Gaussian look to it. So you can see, starting out with a uniform random variable, which doesn't look anything at all Gaussian, by adding 4 of them together, I look pretty Gaussian. Um, Consider on the right hand side an exponential random variable. So you can see this is highly skewed. Right? It does have a peak, but it's got that ridiculously long tail on the right hand side. Again, I centered this one 0 on the mean scale. Um, you can see if I add 5 of them together, now this is actually much more non-Gaussian than the uniform is in some sense. But if I add 5 of them together, that's starting to look like a Gaussian with a rounded out tail. By the time I get 25 of those random variables added together, it looks extremely Gaussian. It's slightly wider on the right hand side, but not very much. So as you keep adding them in, or as you keep taking the output and putting it to another linear system, it's going to get more and more Gaussian. And so pretty much any distribution that gets, you add a bunch of them together, put through a whole bunch of linear operations, addition's a linear operation. That's why this is working, right? Um, but all kinds of things are linear. So when you pass them through, you're just going to tend to get Gaussian functions. So that's kind of pictorially why Gaussian matters so much. Um, this is kind of the key ideas you should keep in your head here is, roughly speaking, you got about 68% of your data is going to fall within one standard deviation plus or minus of the mean. You got about 95% is going to be within two standard deviations, and we usually say about 99% within three. Right? So these numbers are just kind of give you the approximations to them, and you just go further and further out with each one. But you get this nice little curve shape that's on it, and you get this distribution of data. And so it just gives you an idea. The bigger sigma is, the more spread out that Gaussian is. And that's going to be crucial to us. We're going to basically not care so much about mu because we're going to basically force mu to go to zero. We'll calculate whatever it is and subtract it out, and then you can add it back in later on. But we're going to want to do all of our calculations with mu equals zero, which I'll show you why in a second here. All right. Here would be my example for that. So imagine I took now a multivariate Gaussian random variable. So you can imagine in this case, I've got two Gaussian random variables. I've added them together in various amounts, and you'll see that kind of elliptical shape on what it is. That's all of these standard deviation curves. You can see, if you imagine drawing an object around when you got 99% of these three standard deviations out, you can definitely see the elliptical shape that the data starts to form. So when you look at this for any of these multivariate Gaussians, you're gonna get these ellipses. I didn't actually even draw in here because I figured the picture was just so vivid in of itself. You get these ellipses. Now, let's say that we want to, from this, fit a line to it. So this is kind of our first problem. So you can see why I want to actually come in here and put the data centered around zero. So I made my mean equals zero in this case. Again, if my mean was not equal zero, it would be off somewhere else. Like imagine it was in like the second quadrant, the same cloud. If the mean had a positive shift in y and a negative in x, that whole thing would just be moved up into the second quadrant there. That line would not be able to go through the main axis of my ellipse, which is what I really want. So, this is kind of when you're thinking about it. What I want to find with that line is I want to find what the slope is that's kind of going through it. I don't want to find the intercept b. So you can think of the mean as kind of like that intercept, and I'm trying to fit a line. So I really just care about the slope at this point. I don't want it shoved off into that other quadrant because that'll just make it very difficult to fit a line. I'd have to also calculate b. That gets really ugly. So just I calculate what the mean is, subtract it all, I shift it down in here, and now I don't have to worry about it. So subtracting the mean out is kind of our first step that's on almost any of these algorithms. We subtract the mean, we remember it, we do our calculations, you can then add it back in at the end, and everything works great then. It's the much simpler way to handle the problem. So I want to fit a line here. Well, how do I fit that line? Well, we're going to calculate minimum residues. It's hard to tell, but each of those two green lines there is actually going to a red dot. If you look really close, you'll probably hopefully see them. I tried not to draw my green lines to overlap the red dots, but I believe I can see them in there. I'm not going to claim my eyes are the best. It's really easy on the bottom one, but I promise you there are red dots there. So I've just kind of drawn this, but instead of just doing, any of these, imagine I went through on these and I wanted to find what is the minimum residual, the minimum distance from my main green line to all of those little red dots. So imagine I did that calculation, that distance on all of them. Okay? Um, if I want to minimize that residual that was going on, I would then cause that line to shift down so I could try different slopes on my major green line and find out whichever one gave me the smallest distance to all the red points, the smaller green lines. Right? Um, that's going to happen when that green axe or the green line is right on the principal axis of the ellipse of all that those red dots kind of make up. And um, so there we can also talk about maximizing variances that are in here. But um, when you think about all of your data that's in, I can minimize my residuals. That's probably the easiest one for you to picture at this point, right? Shrink those lines, kind of get it to to fit along it. Um, we'll talk. I'll talk in next. There's a better picture for variance here in a sec, right? Um, so if I were to rotate this so that I got the smallest distance, and you can see, um, for pretty much any of the red points, a few of them might be a further distance away, but on the average, the whole thing is significantly um, less distance from each one. So if you want to think of it this way, PCA is basically finding the best direction. So if the left one is kind of my original data, the right one, all my data is still there. I've just kind of been able to rotate the data to be able to figure out what really matters. What is the direction that shows me the correct things for what's going on? If we consider this algebraically, if I put my variables in the columns and I get measurements of data corresponds to rows, assume that I center my data that's on, right? Therefore, the relationship between my variables that I want to find and the measurements that I have are all of these A matrices, or all these values in A. So I can consider all those A's as a matrix. In this case, a 4 by 3 matrix. And I can take that basic data. I want to center all my measurements, and then I can calculate from this the variance and the covariance between my different variables, right? Variable 1, 2, and 3. And the more that I calculate those, or both the variance and the covariance between them, that's going to help me to figure out what are the directions that underlie my data. So far we did a bunch of points, right? Each point is a measurement. And in that case, I just had two variables that I could deal with, right? And so I wanted to find out what was, the best direction basically for those two. Let's talk about how we calculate variances and covariances. They're really, really similar. So a variance is how one variable varies with itself, second moment. So if you consider those columns, AI, right, which is my data on them, right? Um, that's all for one particular variable. I'm going to take a variable AI with itself, AI transposed, multiply them, I get a single number, um, and that's going to give me, that's essentially similar like a squaring operation, just in matrix land. And 1 over n minus 1, n is the number of data. When you calculate standard deviations, particularly for measurements, you don't use n as the divider. Since it's from measurements, you always do n minus 1. Covariance is between any particular variable and another variable in them. So if I want to take a look at how variable 1 and variable 2 vary with respect to each other, how much is that second moment for the combination of them, that's a covariance. So I would take the jth column or the second column, right, with the first, and that's AI and AJ. So AI transpose AJ. Again, same scaling. I can combine those two together by calculating this covariance matrix. We call the covariance matrix C, right? It's got the same scaling factor, except we're now doing the entire matrix, A transpose with A. Now, the reason why I do this is really just to show you why it makes sense for this kind of combined covariance matrix, A transpose A, with that scaling factor of 1 over n minus 1. Well, there's a way that we can calculate this. It allows us to do some nice stuff. If I imagine that covariance matrix is the matrix I'm working with, I can do an eigen decomposition on it. So um, if you remember, eigenvalue is defined as I've got some square matrix, and a covariance matrix is square, right? A transpose times A is square by definition, right? Um, so I've got an eigenvector x for that, which will correspond to an eigenvalue lambda. I'm going to have as many as there are dimensions, so that will allow me to get, imagine x is now all of the eigenvectors kind of stacked one after another, and that's equal to, right, those same eigenvectors stacked times capital lambda, which is basically the eigenvalues on a diagonal. So we can take and multiply by x inverse. X is invertible under, as long as the system is independent. In most cases, we get all this kinds of nice stuff. But assume I've got a full rank system and I don't have any weirdness going on. I can get all these nice independent eigenvectors and eigenvalues. And so I can just invert the eigenvector matrix, and assuming everything is really, really nice, that inverse will be a transpose, which is what the last one states. So if I've got nice orthogonal matrices, I'll get that. So I can do this eigenvalue decomposition. The eigenvectors will actually turn out to be the directions that those we're trying to find, the principal components. And the lambdas will turn out to be the scaling factors. And this is a pretty nice way to do things. It's pretty understandable. There's been a lot done on the eigen decomposition, so lots of good things. The only problem here is actually calculating C. Calculating the C matrix, since you're squaring a matrix, you tend to introduce more errors. So if there's any error inside the original A, when you calculate C, which is A transpose times A, you in essence square the errors. So the errors get bigger. And so you're working, it's really that, not that the eigen decomposition is bad, it's really just calculating C gives you more errors in the system. So we'd like to be able to calculate it without having to do that. So a better way to calculate is using what's called the singular value decomposition. And this is going to be used a lot by us, so it's at least good to know that this exists. It's kind of an extension of the eigen decomposition to non-square matrices. So I can work on the original A. The original A matrix has a singular value decomposition, which is a matrix U times a matrix sigma times a matrix V transpose, where U and V have similar properties and behaviors to basically what X is. A little bit nicer, actually. They're fully unitary, so really good stuff. And sigma is a diagonal one, similar to lambda was. Now, if we consider the C matrix, which is A transpose times A, I can rewrite it using the singular value decomposition of A, and I can find that basically V, right, which is the right of my two singular vectors, right? U is the left one, V is the right one. V is the only one that appears now, but I don't have to actually calculate this from the A transpose A. I can calculate the V and the sigma from A, where I don't have squared errors, and then I can actually use them. I still use the exact same V, and I can use sigma squared, but that's just a square of a number, so the errors are not bad in that case. So it's a lot nicer to calculate because I can calculate before things have been squared, and so the errors are retained. All right. So here's kind of my my quick area to go through this. Um, what I'm trying to do with PCA is I've got a bunch of independent Gaussian variables. Um, I have linear combinations of them. I want to find the lowest dimensional basis, right? I want to find basically the smallest thing that goes in. And this is kind of what we call maximum information. Now, I promised I would explain better why that is. Um, if you think about it in this way, I want to find the way where the line itself is most consistent with the data, right? Um, that you're giving the most information possible. So if you think about that original, see this lovely thing, if I can go backwards a bit. Oh, there we go. Okay. Um, so imagine on this line here, where we can see the data points clustered, we can see the green line, right? Why do I say how much information? Well, right now, this line doesn't give me a great deal of information about this particular distribution, right? Because it's not lined up with it well, right? If it was lined up perfectly, so if it's lined up here, right, the amount of information I'm getting, it's consistent all the way with that furthest to the right red point. You can see how many it's in line with. This green line is giving me a lot of information about what the actual ellipse's shape is. Right? You gain a lot more information about what it is than when you had the not lined up version. Right? So if I had the not lined up version and you saw the information on this, where the red dots fit on it, it would only be a small section. It would only cut through a little bit. So if you imagine the information is kind of like which red ones are correct on this, you're only getting a very small thing. There's even worse directions. If I cut through the narrowest area, you'd get a really small cross section. So that wouldn't tell you an awful lot about how the data is varying. What does give you a lot is if you figure the farthest object that's still a data point on the left to the farthest on the upper right, between those two, that's kind of the maximum spread of the information. It gives you the idea of how much information is there. That's what we call it, the maximum variance. We're talking about which dots vary the most, the furthest in their lines. So cutting through the short way, I would have a minimum variance through there. So maximum variance you can think of as the maximum component, or the longest cut through the entire data. And that's what I'm trying to, when I drew those green lines, I was trying to draw it to the furthest one out there. So I wanted the data points that varied the most. Now, in truth, it's not always the ones that are the furthest out, but it's at least the ones that are most consistent in that whole data run. But basically, that's the idea that we're doing with. I gotta find my way back. Anyway, I want to find that ones that have the biggest information, and variance are kind of similar in our ideas. So the further the data spreads out, the better it is. The solution we said was we took the zero mean. Remember, we didn't want it off in some other quadrant. So remove the mean because we just want to deal with the slope. Then we took the SVD, right, singular value decomposition of this. And, assuming that the variables are in the columns, then the right singular vectors form the correct basis we want to look for. And as an added bonus, those right singular vectors will also project onto the basis. So it gives me a lot of nice stuff. So that solution, I'm going to show you how I can use it. So imagine, here's a smaller set. Two sensors, takes a bunch of data. I want to find the principal components. Oops, sorry. My words cut underneath my picture there. Anyway, so I make a matrix A where I put the X in one column, the Y in the other column, 200 data points. So you can kind of see it. there's my XY. That really is the first several pieces of data from what I generated. Um, and it just keeps on going. Um, there's a command called SVD in MATLAB. So I just took the SVD and I got these three components, U, sigma, and V. I care about the V component, which is kind of telling me the aligned direction. So just looking at the V from that, that is the V that's there, right? 0.8634. And you notice the 1, 1 and the 2, 2 component inside V are exactly the same. And if you see the other ones, they're the same magnitude, opposite sign. That's because this is actually a unitary, well, it's a unitary matrix, and in particular, it's a rotation matrix. And the 0.8634 values, top and bottom, are cosine of a theta, and the 0.5044 plus or minus is sine and minus sine respectively. If you take any of those and you take their inverse trig functions, you'll find the theta value is right around 30. It's 30.29 degrees. Now, interestingly enough, if you were to look at that original data that's in here, I put those at a 30 degree. So it shows and it calculates the correct data. Now, it's only 200 data points. If you get more and more, it would be more and more accurate to it. But already it's doing a pretty good job of telling you the correct piece of information for it. So you can see here, this is the plot of the original. And if I plot, A times V, V is, remember, that rotation matrix, which is the same as plotting U sigma, because V transpose just becomes the identity matrix. So if I plot that, right, V times A or U sigma, right, I just get the rotated version of this, which you can see is nicely lined up along the main axis. So you can see I can find the principal component, the axis where there's the biggest variance in that direction. That's why I'm maximizing the variance in that principal direction. I'm therefore minimizing it in others. So the first component is going to give you the maximum variance, which means the lowest residuals also from the line to the points, because all the information is coming down to that axis. That's the idea. All right, here's a second example. Imagine I took a sine wave and you can see the upper left here is the original sine wave, and then I mixed it by rotating it, right? And the other mixing thing with it is 0. So I just kind of rotated it in 3D and ended up with a rotated version of it. And then I said, hey, I now want to find what was the unrotated, because let's assume I measured this rotated sinusoid coming in, because I don't have my sensing array correctly aligned. And now I want to be able to find out, where is it? Well, I want to find what direction the signal varies the most. So the first one will say, what gives me the maximum variance, the most amount of the signal going in its direction. And I want the other direction to have the least amount of the signal's information in it. So this is a PCA problem. So I calculated exactly the same way I did before, and I just plotted the first principal component the same exact way I did the other. So I literally took, this mixed signal, calculated its SVD, and then plotted the first component, the first singular value and its singular vectors. And what I get is what you see on the left, and then I applied the second one, and you'll notice, even though it kind of looks like it's got noise and whatever in there, if you look at it, it's times 10 to the negative 16th. Right? So the size of this is just ridiculously small. So you're not getting any real data on this. Right? And since it was supposed to be 0, basically it's done exactly what I'm supposed to. It finds out, hey, there really wasn't any other signal there. But principal component 1 found there was a sinusoid. And you'll notice it is the correct sinusoid. All right, so that gives you an idea of what PCA is. Find the principal component, the biggest direction. Independent component analysis is a little different. We're going to assume that the data sources are independent random variables, but now non-Gaussian. So why non-Gaussian? Well, this is actually for the same exact reason the other one assumed Gaussian. It assumed everything had kind of reached its end. It's gone through lots of stuff. But let's say I was trying to work back to the original sources. Okay? Um, if I'm working back to some original sources that might not have been Gaussian at the start, they're going to become more Gaussian over time, which means if I'm going backwards to try to find the original, I've got to make them less Gaussian. So we're going to assume that we're dealing with who knows what that is not necessarily a Gaussian, because not everything is Gaussian in the universe. Oh. And so to get to the original thing, since measurements are going to go through a bunch of linear systems, it's going to become more and more Gaussian over time as they blend. So I need to unblend them, which means I've got to go less Gaussian. So I've got to assume my original things were less Gaussian and work backwards. That's what independent component analysis makes that assumption. To get to the original data, you have to go less Gaussian because things are going to tend to become more Gaussian over time as it's going through different systems. To get back to the original, undo it. All right. We're going to assume that our measurements are potentially even nonlinear sums of sources, and we don't know the sources or the mixing of the sources. So technically speaking, we don't have enough data to do this. Right? So you can just write this off as impossible right now and end, and that's where most people did. But the neat thing is, you can actually still get somewhat of a source. You can't get it perfectly, but you can make a few assumptions, and then you will have enough data, and now you can get some good information. And one of those is this non-Gaussian assumption. Um, the other one can be actually best seen by considering what's called the cocktail party problem. So this was a kind of a first idea that people would talk about to try to say, hey, how could we do this? So imagine you're at some type of a party, and there's N people attending. And, each of them are talking about different things. Maybe they're in different groups around the room, right? And you want to basically be able to separate out each speaker, what they're saying, from the noise. Now, if you've ever been in a crowded room with a lot of people talking, you can hear a lot of people talking, and you can try to home in on somebody and concentrate on them and try to block out what other people are saying. And you can kind of mostly get the gist of it as long as they're close enough. That's kind of your brain doing this exact problem. And we're going to assume instead we've got M recording devices. Imagine, M microphones spread around the room, and that we have at least as many microphones as speakers, maybe more. But at the dead minimum, you must have as many of these microphones as there are speakers. You can even give me more microphones than speakers. You just can't give me less. And we got to assume everything is all spread. And then now we've got all these different recorded sound waves, and we want to undo this. Right? The people are spread in different areas. We don't know where they're located. I don't necessarily even know where all the microphones are, but I might. And as each person's talking, if I'm closer to the microphone, in theory, I would be heard better. But every microphone's going to get some superimposed version. So it's going to see some people a little bit louder than others, but it's going to get a combination of everything. Right? Now, how can we go about doing this? Well, we draw the first thing from what we said with PCA. We got to remove that mean, right? Because we want to get right to the center. That reduces trying to figure out the biases. So we calculate the mean, remove it. And then what we want to do is say whiten the data. The idea with whitening the data is your data, is not necessarily kind of in its best format when it's on. So we want to kind of clean it up and get everything scaled nicely, right? Say for instance with the microphones on my speakers, I, the different microphones could have certain different amplification factors and things of this sort, right? So let's say, for instance, that one microphone had a really good gain and the other one, its battery was dying, so it was a little weaker. I, I don't want to deal with the amplification difference on these speakers. I want to make it as if every one of the microphones had the same signal strength. I'm, now, that's not really true in real life, but if I can do that, I've removed part of the challenge of my data by assuming they all measure the same amount, and I can do that by measuring them and adjusting the volume levels so they're all correct. And I don't have to worry about volume levels in my problem. And I can assume that the sum of all of my things adds up to one, and that reduces some of the complexity. And the other thing I can do is reduce the dimension of the data. So let's say I took PCA and I looked at this, I could find out how big things vary. Well, it could turn out, like, let's say I had, 50 microphones, but there was only 30 people in the room. And, um, you're going to find out you potentially you're looking in a 50-dimensional microphone space, but you've only got 30 dimensions worth of person data. So I can reduce the dimension of the data so that I can deal with just 30 microphones worth of data that are the best examples of measurements of my 30 speakers. So PCA can be used. You can do other things as well, but this is why I said PCA comes in nice. I can do that PCA to kind of do my first condition of the data. I can find the right size of the data. I can adjust the volume levels. We always zero the mean first as part of PCA. So those kind of first several steps do this. In truth, PCA can be thought of as a preconditioner, that fourth step. But I can also do some other preconditioners if I want as well to try to take care of some nonlinearities or do other types of adjustments in there, or to make my data a little bit nicer. Very often, what we'll do is we'll actually take and try to do some cheap initial calculations that'll give me a better starting point, things like this. And we'll talk and show about that as we're going through the algorithms here. And then we're going to do an iterative algorithm to try to separate things based out on a cost function. What that means is we're going to take a guess, and then we're going to take a look and see, based on some cost function we'll choose, are these sufficiently different? Right, so remember, we're trying to extract out different signals, and we're assuming that they're not Gaussian, and we want to assume that they're fairly different too, because you in that cocktail party you could have one people who are talking about, you know, where they were traveling, and some other people might be talking about a book they read, and some other people might be talking about some funny story from their past, right? But all these things, they're pretty different from each other. So what we want to do is, since they're not all talking together, they're in little clumps talking on different stuff, we want to separate them out because each person's going to have a very different voice and a different subject matter and things like that. So we want to minimize the mutual information, what they have in common, or we want to maximize how non-Gaussian they are. Those are the two basic cost function families that we try to figure out. And we do this iteratively. We take a guess. We think these are our 30 speakers. And then we see, was that correct or not? Is there a lot of mutual information? And then we just try to move in a direction that will minimize the mutual information or maximize how non-Gaussian they are. We just change them a little, we test again. We change them a little, and we test again, right? And this is the idea of an iterative algorithm. You won't necessarily get to the final answer, but you'll get good enough. And that's really the thing, just small steps in the right direction to separate them out. These type of iterative algorithms are slow, but they tend to work well. Um, so let's talk about some of these cost functions, right? Minimizing the mutual information. So we have available distribution or available data. And there's a bunch of distributions that might fit it because we don't have that much. So um, we want to be able to find um, one that maximizes either, and typically for mutual information, information is related to entropy. So we can either do relative entropy, such as the Kullback-Leibler divergence. Right? If you notice, it's got that minus sum of p times log, and then it's got a relative quantity of q and p. So that one's trying to find the relative entropy between p and q. and you've got that classic P log something form. Or you can just maximize the standard entropy form, right? The minus sigma P log P. Um, and you do that over each of the different functions. In this case, it's I is your different ones, right? So I've got, you know, I could be like 5, right? So I could have, or in our case, 30 speakers, right? So each of those, I would have 30 different functions P, and I could calculate the entropy for each one. And I want to end up by making these small changes causing that value S to increase, or causing, you know, DKL to increase between those two different, in this case, P and Q, or you could even put it as, PI and PJ if you wanted. Right? So that's kind of our ideas of entropy. Remember, entropy is basically information. We want to, minimize the mutual information between them, which kind of maximizes the total amount that's here. Um, the other thing I could do is maximize the non-Gaussianness. Now, non-Gaussian can come in a couple different forms. Gaussians don't have any skew. It doesn't tilt left or right. So I could try to maximize the skewness. Now, if it's not a skewed function I'm dealing with, maximizing skewness could really mess things up. But if you are dealing with skewed functions, so this is kind of like, you know it, skew is basically a scaled version of the third moment. So calculating that third moment, well, the third moment is 0 for a Gaussian. Um, so I could have, positive or negative skew, right? Is it skewed left or right? Skew can help me. I can try to maximize the skewness, but again, skew can also cause the thing to go really ugly if you're not dealing with a skewed function. Kurtosis is kind of like how it deals with the tail. The easiest way to talk about it is that the tail is either fat or thin. Right? Fat tails tend to mean that you're gonna, um, you get larger and larger, like chi-squared. Right? You can get extremely out there events that can happen with reasonable frequency, whereas Gaussians, really extreme events are not likely, and essentially diminishing that you'll get some extreme event. A fat tail distribution is very like thin tail distributions. Extreme events are basically impossible. So kurtosis is kind of saying how likely is the really out there events. So it's a fourth moment area, which again, fourth moment for a Gaussian is 0. So that's Gaussians only have non-zero first and second moments, and we knock out the first moment. So for our Gaussians, we're really just dealing with the second moment, the variance that we're trying to calculate. So skew or kurtosis, right? They're different assumptions. So if you have a skewed distributions or a reason to assume they're skewed, then use skew. If you believe that there's, either a really much fatter or much thinner tailed distribution, then kurtosis is good. Like if I was dealing with a strict unitary, it has really no tail. So that would be an extreme example of a thin-tailed distribution. So kurtosis would be a very good measure for that. It, uniform distribution would not be good for skewed because it's not skewed. So if you maximize skew, you're not going to get a uniform distribution out. So you have to kind of know something when you're picking what you're maximizing here. Some assumption about it has to go into what's the right direction to walk. You can also walk in the direction of negative entropy. Right? You can think of negative entropy as the distance to a normal or Gaussian form. So the entropy of a Gaussian, right? Say mean distribution. That's take the minus the that entropy. It'll kind of walk you away from it. So neg entropy is another option. I mention these because when you deal with MATLAB functions, whatever else, they're going to let you choose a function to use. So these are some common ones. Okay, let's take a little walkthrough of how this whole process can work. So let's imagine that this is kind of my original setup, right? I have X, Y from independent random variables. So I make, X is a uniform and Y is a uniform, and I get a bunch of points that have X, Y, and they're uniformly distributed. And this is MATLAB. I just uniformly calculated X and Y, put a bunch in. You can see it's uniform. You get this nice little square. Um, and then what I do is I mix them, right? Which essentially is kind of basically a rotated system that's on. But you get a bunch of data, and you can see this one's been rotated, and it's also been kind of tilted and skewed a little bit. But you can see that you've got your basic information in here, right? The question is, how do I recover the original setup? So first thing I do is zero mean and whiten it. So if you look, it's pretty close to zero mean, but it's by no means scaled nicely. So um, I run this whole thing through PCA and let it kind of zero the thing out and get me a nice scaled version. So this is just down to both directions. You can see it runs from -5 to 5, both on X and Y, which um, it wasn't really scaled like that. If you notice, it's my Y was like -40 to 40, but my X was running like, -70 to 70. So they weren't scaled the same. So I ran through, my PCA thing, and now I've got everything scaled nicely. That's what we mean by whitening it. All channels get equal amounts uh, of value to them, right? I'm not weighting one thing more than another. So another one is kind of just saying treat all of them the same. That's all we're trying to do with it. All right. Now, let me walk through kind of what this looks like. If I take this and do a histogram, so I take each of these kind of ranges, you can see the kind of tick marks. If I count how many of those points occur inside its range, and I did for both X and Y, I just did a histogram, so everything straight above any of those little columns. So you can see the little histograms on the x-axis, for instance. Uh, the first little kind of range in there has very little data, right? And I centered them on the tick marks. So if you're closer to, that first tick mark, boom, there's almost none in there. But if you're in the middle areas, you can see it's huge. So that's basically what I did with each one of these. I made a histogram and I kind of plotted them. And um, so you can kind of see what the data is. And you can see it kind of forms these kind of Gaussian look to them because there's more in the center, right? So if I was counting a row that's kind of in the middle area or a column in the middle of the distribution, I'm going through a lot of data points. Where I'm on the extremes, I'm only kind of going through that little triangular chunk that's left over. So, there's just more points kind of towards a cut in the middle, either vertically or horizontally. That's what those histograms are showing. Now, if I were to rotate all of these points, you would imagine my distribution would change. So I keep rotating it until I find the one that looks most uniform. Rotate, 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 and you can see here that when I line it back up with my perfect little square, I get the most non-Gaussian I can. It looks pretty much like a uniform. It's not perfect, but remember, I only have so many data points in here. If you had more data points, it would be a better distribution. But this is as extreme as it can get, and that's the correct answer. That's really what the idea is. It's just a little incremental. It rotates a little bit each time, and it just says how Gaussian is the x and y direction. And as soon as it gets the most non-Gaussian, these close to two uniforms, it says that must be it. And in fact, it is it. All right. So here's a simple example, right? I took a sinusoid and some random noise, and I added them at different values. So you can see the first column is your measurement, and it's got a lot of sinusoid and a little noise. And the bottom one has less sinusoid and a lot of noise, kind of thick, chunky, right? Um, Now the reality of what the original signals are on the far right. You can see the column called true. You can see the actual original sinusoid and the original noise. Now, if when I run this through ICA, you can see I get a sinusoid out. And if you notice it, the sinusoid I get is just a negative of the original, and it's scaled a little bit differently. But remember, my scalings, I said I don't care about the scalings. I whitened it. So I changed the original values. So it's not necessarily as big as it was because I can't get the size. I'm just trying to get the shape. So this is one of those things where I said you can't get all the information. Well, one of the things you can't get is the scaling factor. But if I get the shape of a sinusoid, and plus or minus is also a scale factor to me. So the fact that the shape I get for the sinusoid in ICA is negative of the true one doesn't matter. If you took your ICA and flipped it and scaled it down a little bit, you would get the true one. I call that a win. So if you were thinking in terms of a person speaking, all this would say is you basically the difference between my two things would mean what I get back, the person would be a little louder than they really were, but you would actually get their actual voice. And if you look at the noise is also just a flip. So it's pretty darn close to the actual noise, but it should be negated. But again, that's completely legit. We have no problems with that. So differences of plus or minus or scale factors, not a big deal to us, as long as the shape is correct. Okay, so we say that's kind of a win. It worked well. Here's one more example. A sinusoid and a sawtooth. If you look in the far right column called true, you can see the sinusoid and you can see the sawtooth. They have drastically different periods and everything else. Um, if you look at on the far left, the measured or the data that was supplied, you'll see basically a sinusoid with a small sawtooth on top of it, kind of making this chopped up sinusoid. And you'll see right below it one where it's mostly a sawtooth, but it's kind of waving up and down with a sinusoidal beat. I put it into ICA, and you can see I pretty much get, again, there's a negation factor in, but I almost get a perfect sinusoid. You can still see a little bit of some kind of notches on them from there. I could let it run back in and let it calculate some more, and those will get smaller and smaller because remember, it's iterative. It's not going to give you perfection. It's going to move towards the correct answer. So I can take those and I can get them a little better each time, um, and it'll get smaller and smaller. But you can already see it's moving towards the sinusoid, and it's done a really good job of pulling the sinusoid out and giving me the sawtooth wave. So those two combos, you can see it pulls it out. It will not necessarily tell you them in the right order. I showed you the order it guessed them in. It found the sawtooth first, and then it went for the sinusoid. Um, so, um, therefore it put the sawtooth first. But that's not a problem, right? You can easily kind of match up which one's which. So that one shows you how it can work. Now, I didn't put this on a slide because this is kind of really why do we want to talk about this? Um, we are going to be measuring EEGs and working with them. Well, an EEG is a bunch of electrical measurements all around the outside of your skull, and there's a bunch of different sources producing different thoughts on that in different areas of your brain. So you can kind of think of the different areas of your brain, like your whole brain is a party. The different areas are the little conversations that are going on, and all these EEG things are microphones around the outside of it. So basically, your brain is our cocktail party. We take a bunch of EEG measurements and we want to find out what was the thoughts or the regions of activity when you're thinking that go on, and to try to get them back. So from these outside measurements, we want to find out what areas are activating and how are they activating. Basically, you've got this same, that's sometimes called a blind source separation problem, or um, an independent component analysis one. So basically, we're going to be able to take our uh, EEG data and do the ICA calculation problem, and we'll find out what regions, that's how we'll find out the regions of the brain that are activating, and in what way is it activating. So this is kind of the math that underlies all of it. So at least you've got an idea how it's working. You can see, you know, it's not perfect, but it does a really good job. It'll clean things up pretty well. The more complicated the thing, you've got to have some idea about what you're getting. Otherwise, it won't step in the right direction towards a correct answer. And it iteratively moves. So if you're not getting something good, you might have to adjust, what is that cost function you're picking? And you might have to run it longer to do more and more iterations to converge to a good answer. But at least you've got an idea how it works. So hopefully that helps, and I will talk to you all on Tuesday. And I get to see if I can pause this lovely thing there.